So now that we've done all of our steps 1 through 5, we can now move on to our regression, so step 6. Now, just as a reminder, regression provides additional details over and above correlation. We're doing simple linear regressions today, and there's actually a lot of overlap between simple linear regression and correlation. You can actually reproduce all of the correlation statistics in a simple linear regression, and I'll highlight this today. Next week we move into multiple regression. We lose this because we start to get into some more fancier aspects of regression, but today the two are very similar. The one thing that the simple linear regression will provide over and above correlation is that we get additional details that actually allow us to start talking about prediction. So for example, we're now going to get an R-squared, which is going to talk about how much variance in the DV is explained in the IV. Or in other words, how many of the reasons why different projects got different project scores, different ratings by the judges, can be explained by a single IV. We also get overall model statistics. Now, these really aren't too important for today, but are very important for when we get into multiple regression next week. So I'll bring up these very, very briefly today, but we'll spend a lot more time next week on them. We're also going to get something called a beta statistic. We also get confidence intervals around this beta. And these confidence intervals really give us an idea of the range of betas that could be. And we'll talk more about this in a second. We're also going to get t-statistics and p-values that are attached to these t's. So there's lots of information in this regression that we don't get in the correlations. Now, regression is a hypothesis test, so it does have a null hypothesis in the same way that correlations have a hypothesis. For regression, your null hypothesis is that your beta is going to equal 0. So I said here you get a beta statistic with confidence intervals. We'll talk about what this means and how it relates to the null hypothesis when we get some output. But really the null hypothesis is saying that this beta statistic equals 0. That's what we're testing against. Just as a bit of a note about notation, you can write up null hypothesis as H0. So if I was formally writing a null hypothesis, I would say H0 colon beta 1 equals 0. That's how I'd write this up. Okay, so let's move on and get some output, because then we can actually start talking about this a little bit more. So we'll talk about the regression equation once we've got some data, but to actually produce our simple linear regression, we use the command regress. Then we have our DV, which should be rating, not ratings. And then we have our IV, research. So unlike correlation, our regression command starts distinguishing DVs from IVs. And so I guess essentially the formula is regress, DV, and then IV. And when we move into next week, we'll see that you can have as many IVs as you like, but only one DV. So the first variable that comes after the regress command, Statter is taking that as your DV. Okay, let's run this. So this is what our regression output looks like. This up here is called an Anova Table. I can see that there are 24 observations, so there's no missing data. I get an F statistic of 8.28, so this is my overall model statistic. Again, it's not too important for today, but we will come back to it next week. Interestingly, though, the significance of my overall model, the p-value attached to that is 0.0088, so this is below 0.05. Effectively, what this p-value is telling me is that my model, whatever IVs are in my regression, so the IVs that are in your regression together, we call this a model. And in this case, our model is simply using research as an IV on its own. Then I can see R squared underneath. Now R squared represents how much variation in the judges' ratings can be predicted by research, or can be predicted by the IVs in the model. In this case, we have just the one. Now, and another way of thinking about this is how many of the reasons as to why a person got the rating they did on their research project can be explained by how much time they spent researching for the project. And R squared is expressed as a score from 0 to 1, 0 meaning 0% of the variance or 0% of the reasons, 1 meaning 100% of the variance or 100% of the reasons. In this case, our R squared is 0.2734, So what this tells me is that 27.34% of the variation, or the reasons, why a project got the score it did is due to how long the student spent researching for the project. Now, some interesting things at this point. If I took the square root of my r squared, so where's my calculator? So my r squared is 0.2734. If I take the square root of this, I get 0.523, or thereabouts. Now, if I go up to my correlation matrix, interestingly, the Pearson's R between ratings and research is 0.523. So this highlights an interesting relationship that's worth noting, that R squared equals Pearson's R literally squared, and similarly Pearson's R equals the square root of your r squared. So you can actually go between the two. So if, for example, I was asked the question in a quiz or something like that, if I have a Pearson's R of 0.5 between two variables, how much variance do they explain in each other? I could simply square that Pearson's R, and that will give me my r squared. And then I could say, well, this is how much variance they explain in each other. So you can move between the two. Now, another thing to take note of is that my p-value for this correlation was 0.0088. It is by no coincidence that I get the exact same p-value in my model statistic. And the reason for this is that simple linear regression is just correlation. It's the same thing, just more detail. Okay. So there are two connections. And just between those two statistics, we've already reproduced all of the data in our correlation. Now that this is significant, let's move down and actually look at this bottom box. And the things that we're going to be interested in is this research line. And we're going to talk a little bit about this -16 and what it represents. So first of all, let's just go through the different columns and talk about what we have here. CoF is our regression coefficient, or a beta coefficient. And so each variable gets one of these. So in this case, research has a coefficient for 5.75. We also have a standard error attached to that coefficient to try and capture how much variation is there in this measurement. And we'll talk about what this is in a second. We also get a t statistic and a p-value attached to this t. And this is our significance test. And we also get confidence intervals around our coefficient. So again, we'll talk about what all this means in a second. Something to note just from these two. First of all is your p-value here is 0.009. If I round this p-value here to 3 decimal places, I would get 0.009. They are the same p-value. Similarly, if I take my t of 2.88 and I square it, I get 8.2944, which is exceptionally close to my f. It's within rounding error, and seriously, what's a few decimal points between friends? If you take the square of t, it gives you f, and similarly, if you take the square root of f, it gives you t. So this gives us our next little formula to take away from this. T equals the square root of f, and f equals t squared. And so again, you can go between the two. So if I was asked, what is the f statistic associated with the t of blah, I could just square the t and get its f. They're the same number. However, the relationship between t and p and f and the p of f only work like this in simple linear regression. And we'll see next week that when we move into multiple, that this doesn't hold. Okay, so let's talk about what's down here, and then what do these numbers actually mean? So I have two rows. I have a row for research, so that's our IV of interest. And then I have a row for something called underscore cons. Now, I didn't ask in my syntax for underscore cons. Status just put that in there. And this is actually quite important. Underscore cons represents what's called the constant, the intercept. And this is going to represent the DV score that I would expect to get, or I would predict to have, if my IV equals 0. So if I had a score of 0 on research, what judge's rating would I expect to have? So another way of saying this, if we put it more in real-world terms, based off this analysis, what judges' ratings would a student get on their project if they put 0 hours into their research? That's what the intercept represents. It doesn't matter what this is. It's always, what is the expected DV score when your IV is 0? And this coefficient is that exact number. So based off this model, it's expected that a student who spends 0 hours researching will get a judge's rating of -16. Now, that should already be ringing alarm bells for you, because the judges' ratings are on a score of 0 to 4. You physically could not get a score of -16. This is an issue to do with the fact that the odds are we don't have any data of people doing research having less than 0, or having even 0 hours. And if we look at our data just for a second, just looking down here, I can see a 6.5, I can see a 6.1. So the minimum time spent was 6 hours. So we don't have data about the projects, about the ratings that we would get for a project that has 0 hours. We're basing it on data from between 6 to, I think it's about 11 hours. So a 0 on research doesn't actually make sense, yet that's still what the constant represents. And whilst the 0 on research doesn't make sense, we'll see in a second that having the constant set there still is actually beneficial. There are things that we can do to make this constant make more sense, but we'll talk about that in the future. So the takeaway message is that the constant here has a coefficient of -16, and this -16 is the predicted dependent variable score, the predicted rating for a student who did 0 research, who had 0 hours of research put into their project. We expect them to get a rating of -16. It doesn't make sense, but that's perfectly fine, and we'll talk about why that is in a second. For the purposes of 248, we don't care about any of these other statistics for the constant. We only care about the coefficient. Now let's move to research. The coefficient for research represents how much a rating score changes for a 1-unit increase in research. So in other words, what's the difference between the expected ratings when research equals 0, so -16, and the expected ratings if research equals 1? And then this number here represents the difference of the two. So if I add these two coefficients together, this will give me the expected rating for a person who put 1 hour of research into their project. So if we do this just quickly, -16.35 plus 5.75. So a person who put 1 hour of research into their project would be expected to have a judge's rating of -10.6. Again, this doesn't make sense to have a score of -10.6. This is partly because we don't have any data for anyone with a score of 1. So again, we're making this prediction based off the rest of the data that we do have. But this principle, this idea of our coefficient for research representing the 1-unit increase, how much the rating score is changing for a 1-unit increase in research time, and the constant representing the expected ratings when research is 0, these two pieces of information actually go together to create what we call a prediction equation. So this is our regression equation, or a prediction equation. In its most simplest form, for simple linear regression, is that our expected y, or our expected DV score, or the predicted DV score a person will have, equals alpha, or a, or their intercept, or their constant, whatever you'd like to call it, plus their beta score x. And here x represents the score that they got on their IV. So just to make that clearer, E brackets y is the DV score predicted by the regression. So based off the regression formula, based off this, what's the DV score that we expect a person to actually have? So that's what that EY is. It's the predicted score. It's the outcome score. The alpha is also known as the A, the constant, the intercept, and it's the predicted DV score when the IV equals 0. So it's the predicted ratings of a project for a student who put 0 hours of research into the project. And then the beta is the amount of the predicted DV score increases for a 1 unit increase in the IV. So another way of saying this, if you're more mathematically minded, is beta is the expected DV score when the IV equals 1 minus the expected DV score when the IV equals 0. Take away either of those two explanations, whatever makes more sense to you. I'm about to show it graphically as well. And then we can actually just multiply our beta score by some value of x, some value of our IV, and add it to our intercept to start predicting scores of our DV. So if I was to put in numbers from our analysis, and if I do this, I can actually see them, the formula that I would come up with would be the expected ratings equals negative 16.35 plus my beta for research, or my coefficient for research, which is 5.75, times whatever research score that I wanted. So the example that we used earlier is if I wanted to predict the expected ratings of a project that had, say, 1 hour of research, I'll go 5.75 times 1. Doing the maths, this becomes equals negative 16.35 plus, now if I did 5.71 times 1, I would get 5.75. And therefore the expected ratings is 10 point whatever it was that we had before. 10.6. Negative 10.6. Now if I wanted to say, predict, well, what's the expected ratings of a science project that had 10 hours of research? I would simply change my 1 to 10. 5.75 becomes 57.5. And now I can put this into my calculator. Negative 16.35 plus 57.5 gives me an expected rating of 41.15. Now this makes sense, right? Ratings is on a scale of 0 to 50. So it makes sense that a project could have a rating score of 41.15. And we can do this for any number that we want, right? Okay, so what does this look like visually? So effectively, we can express our regression line as a scatter plot. We can have a line of best fit. Let's say it looks like this. And along our x-axis here, we have our IV. So in this case, our IV is research. And along the y-axis, along up here, along my y-axis up here, I have my DV, which is ratings. Okay, so what this line here is representing is that as scores on research go up, so do my scores on ratings. This is obviously not to scale, this is just to give a demonstration. Now, as good practice, the point at which my y and my x-axis meet, so just here, should always be 0 on each. Actually, let's use this. Let's make this look as tidy as possible. 0. So this is 0 on ratings, 0 on research. And just to make things really, really clear, let's say a score of 1 on research is there, and then let's say a score of 2 is there. So this is a really, really... Sorry, let's make that closer to where the line actually ends. Say there. So this is just a really small part of the line. It's obviously not to scale. This is just for demonstration purposes. But effectively, what the regression formula and those coefficient statistics are representing, the point at... Isn't that fantastic? Let's try that with using the right tool. The point at which our regression line, so this black line here, cuts our y-axis, so cuts here, right? This point here. This is our alpha, our A, our intercept, our constant value. The other way of looking at it is if I go along my x-axis for research and find 0, and I go up to my regression line, that's my intercept. So before, when I was saying that your A, your intercept, your constant, represents your DV score when your IV equals 0, I literally mean if I was to draw this line of best fit and find 0 on my IV, it's whatever my y-axis value is. It's whatever my DV score would be. Now, we also said that our beta represents how much our DV changes for a 1-unit increase. So what's happening here is we go, okay, let's go all the way out to 1 and then all the way up here. So this distance here is our beta or our B, it's our coefficient score. It's how much of a difference there is between these 2 points. And so for us, on our regression, we know that for 1 hour of research, it was approximately negative 10.6, whereas here, the intercept was negative 16.3 or thereabouts. And that was giving us a beta of about 5.3, thereabouts, something like that. And if we go back, I can actually just confirm. Okay, 5.75, a little bit off. So this difference simply represents what's the difference between these two values. So I've tried now to explain, based off the statistics, what they represent. I've tried using the formula, and I've also tried using a graphical layout. So that's 3 different ways that you can talk about what these coefficients mean. Take away from that whichever one of those definitions works for you. Now what we can do with the beta is we can come out here to the next point, in this case 2, and go up. And this would have the same beta value, so that same 5.7 increase. And then for 3, it'd be another 5.7 increase. For 4, it's another 5.7 increase. And this continues going up the line. So for every 1-unit increase, we'll see this in research, we'll see the same amount of change in our DV. Now this is what we mean by a linear regression, in that we assume that every single unit increase in our IV produces the same unit increase in our DV. So in this case, for every 1-unit increase in research, we assume our DV is increasing by 5.75. Now when I say we are assuming that, this is actually the assumption of linearity, and it's one of the formal assumptions of regression. And we'll come back to this in a minute, but this is just to highlight why that assumption is so important, because it's the underlying premise of a linear regression. Okay, let's go back to our numbers. So this is what our coefficients represent. The constant is when our IV equals 0, what's the DV score, and then for research, the coefficient is how much the DV is changing for a 1-unit increase, and then we can use these 2 statistics to predict any rating score we want, using the regression or the prediction equation. The standard error for research represents how much variation there is in terms of standardized errors, and this is more formally captured using confidence intervals. So these confidence intervals represent the 95% range of coefficients that we see in our data. And these are constructed based on the standard errors. So they're not the literal 95% confidence intervals, they are engineered based off another statistic. But the idea of this is if we were to sample the entire population, so every single student that went to any science project fair ever, what this 95% confidence interval would represent is 95% of the scores that we would see, effectively. And this 95% is the 95% middle score, so it takes the mean, effectively, the middle point of our distribution, and goes out from there evenly either side. So if I was to draw it, don't save that, here's my distribution. Let's say this is my middle point. The confidence intervals are going to effectively represent 95% of the distribution in the middle point of it. Now, as a rule of thumb, if the null hypothesis falls in this confidence interval, and remember for regression, the null hypothesis is that our coefficient, our beta, equals 0. If this range of scores includes 0, you'll get a non-significant finding. Because what this means is you can't say with 95% confidence that the null hypothesis is not in the data. It's not possible. This is the equivalent to saying that there is less than a 5%, or there is more than a 5% chance that you could get a coefficient of 5.75 when the actual coefficient is 0, when the null hypothesis is true. Now that kind of wording is how we're going to conclude later on, so that's why I'm sort of bringing that in here. But if 0 is not in this confidence interval, we'll have a significant effect. And by 0 not in the confidence interval, I mean, in this case, both values should be positive and positive, or negative and negative. So this here is our lower bound, it's our lower score, and then this is the upper score. So here we can say that within 95% of our data, our lowest score is a positive value and our highest score is a positive value. So 0 isn't in the confidence interval here. 0 isn't in this range. And lo and behold, we have a significant p-value. Now, although I said don't interpret the other statistics for the constant, just as an example, here we see that there is a negative value for my lower bound and a positive value for the upper bound. So what this means is 0 is in this confidence interval. Lo and behold, the p-value is non-significant. So this generally holds for any test. Okay, so this then brings us to our t-statistic. Our t-statistic effectively compares two things together, and all it's asking is whether or not the expected DV score when the IV equals 0 is significantly different to the expected DV score when the IV equals 1. Or in other words, is this 5.75 unit increase a significant increase? Now, we will talk more about what t-statistics are when we get to Anova, but this is as simple as you need to understand it for now. This t-statistic is simply asking the question of whether or not this 1 unit change of 5.75 is a significant and meaningful change. If our p-value is less than 0.05, the answer is yes, it is. Okay, so here that's what we're seeing. Now let's very quickly go through and do that again for our other regressions, so we can look at rating and build. Here we see that our p-value is non-significant. This is not surprising given our correlation. We can see that our R² is 13%, so 13.3% as explained. And then we can see that for someone who spent 0 hours building, their expected rating is 20.5. That's actually really, really high when you think about it. And for every 1 hour increase in building time, their rating would increase by 0.5. The associated t-statistic is 1.82, and this is non-significant. And this is further conferred by the fact that our confidence intervals have a negative and a positive value. So in other words, 0 is in the confidence interval. Okay, And then let's very quickly do our other regression. And here we can see we have an F for the model of 17.03. It's significant. The level of innovativeness of the model explains nearly 44% of the variance in the judge's rating. We can see from our intercept that a project that has 0 uniqueness or innovativeness will get a rating of 15. But for every 1 unit increase in innovativeness, the rating will increase by 8 units. The associated t-statistic is 4, and that's a highly significant p-value. And again, this is conferred by the fact that our confidence intervals are both positive, so 0 is not in the confidence interval.